Today we are going to study about Kepler's third law. Kepler's laws deal with planetary motion, that how planets move around the sun or how a satellite moves around a planet. And we know that the planets, they move in elliptical shapes, in elliptical paths around the sun. Or if we're talking about satellite around a planet, then it is also traveling in an elliptical path. But we also know that if there is an ellipse, then it has these two axes. This is the major axis and the smaller one is the minor axis. And it is given by a symbol A and B. And ellipse has a property which is called eccentricity. And eccentricity lies between 0 and 1. And if eccentricity is equal to 0, it means that A will equal to B. And this means that if A and B are equal, it means it will be a circle. So it means that circle is an ellipse with eccentricity 0. So circle and ellipse could be talked about together. Sometimes we can use this condition, and so an ellipse will turn into a circle. Now suppose that a planet is moving around sun in a circular path. And let us say that the sun has a mass of ms, and planet, let us say we're talking about Earth, so it has a mass of me. And it is moving around sun, let us say counterclockwise. And it is moving with a velocity at a particular moment. Let us say it has a velocity which will be tangent at this point. And the velocity doesn't change, so it has a constant magnitude. The direction is changing, but velocity magnitude is constant. And this distance, let us say this distance is r. Now this becomes a simple problem of circular motion, where an object is moving around sun with certain velocity, with a constant velocity. And because it is a circular motion, there will be, and because the magnitude is constant, so the tangential acceleration will be 0. There is no force along the tangent because velocity is constant, but there will be force which will be along the radius. And this force will be the centripetal force. Now this centripetal force is equal to the mass of the object that is rotating into the centripetal acceleration. And this could also be written as, because we know that centripetal acceleration is given by v square upon r, so it could also be written as v square upon r. So this is the final expression we get. Now we also know that because it is a problem which contains two masses, and if there are two masses, if you remember, then if it is m1, it is m2, then the force of attraction between them, if it is Fg, and this force is equal and opposite, and both masses apply the same amount of force towards each other. So Fg magnitude will be capital G m1 m2 upon r square, if r is the distance between them. And this Fg is same for both of them. So if this force is Fg, then this force will also be Fg. And the magnitude is same, directions are opposite to each other. So this will be the gravitational force acting in between these two masses. So if we use it here, then the gravitational force could be, so the gravitational force between these two masses will be capital G ms me divided by the distance square, so it will be r square. So along the radius there are two forces that are acting. One is Fc and the other one is Fg. So now we can use the force equation here. So all the forces will be equal to mass into acceleration, or Fc, because the acceleration provided in this case is because of the centripetal force or centripetal acceleration. So it will be MAC. And the only force acting is the gravitational force, and they both are acting in the same direction. So this Fc force will be equal to, the acceleration being provided by Fc will be equal to the gravitational force between the two. So we can say that the gravitational force will be equal to MAC. So we can equate these two formulas. So what we get is that GMSME upon R squared will be equal to mass of Earth V squared upon R. So ME will cancel with ME, R will cancel with R. So what we get from here is GMS upon R will be equal to V squared. Now when we're talking about this velocity, then this is the velocity to go through this entire distance, and this entire distance of which Earth will travel in a particular amount of time will be, so the distance traveled by Earth will be 2 pi r, the total distance traveled by Earth, and the time it takes to go around one circle is called time period, and the time period of this movement is capital T, and we know that it is moving with the velocity v. So velocity v will be, if we are talking about total distance upon total time, it will be equal to v, or any distance. If we are taking only a small amount of distance and we know what time it takes to reach from here to here, that will also be equal to v. But if we know the entire distance and the entire time, that will also give you velocity. So it will be 2 pi r upon capital T. So now let us replace it in this equation, and what we'll get is GMS upon R will be equal to V square. So it will be 4 pi square R square upon T squared. So from here we can say that T squared will be 4 pi squared upon GMS R cube. And this entire quantity, it is a constant, because 4 is a constant, pi is a constant, g is a constant, and mass of sun will be constant. So this entire quantity is a constant. So what we conclude from here is that T squared is proportional to R cube. It means that the time period of the object which is rotating, or the planet that is rotating, depends upon radius cube. So if we have a problem where, if like in this case Earth is rotating around Sun, so in this constant you have mass of Sun, but this entire relation is independent of mass of Earth. In the similar manner, if you have a situation where Earth is the central mass and around it is rotating the mass that is rotating is moon. So if this is the situation, then instead of this constant will be T square will be 4 pi square divided by G mass of Earth into R cube. Because now in this case sun was at the center and Earth was moving, while here Earth is at the center and moon is moving. So if it was sun here, it is Earth, the role that was played by sun here, the same role is played by Earth in this situation. Then this will be the relation, and ms will be replaced by me. Also, if a certain situation, the contour it is not a circle. If it is an ellipse, the path traveled by the planet or the satellite is an ellipse. If it is an ellipse, then instead of using r, we replace it by semi-major axis small a. So we have to replace r by a, and a we know is semi-major axis, length of the semi-major axis. So these are few things we need to understand here, that this the mass which we're using here depends on what is at the center, first thing. And the second is that if it is an elliptical orbit, first do the calculation for this circle and then you can replace small r by a.